Good morning, everyone. I'm Xinyu Shi from China Building Materials Academy. In recent years, the emission of carbon dioxide is increasing rapidly since many countries began industrializing. This intruder gas will do great harm to the steels in constructions of reinforced concrete, like buildings, bridges, and dams. It is said that the carbonation issue is the skin cancer of concrete. Therefore, how to predict the carbonation depths is becoming more and more important. Today, my presentation is a modified numerical model to predict carbonation depths. It's a modified model mainly based on Benzant and Cetus research. This modified model contains 5 control equations. 3 of them are partial differential equations that control the multiphysical fields of heat, moisture, and carbon dioxide. The other 2 equations are ordinary differential equations that control the relative carbonation degree and the equivalent hydration period. These 5 control equations are the most important base of this model. In these equations, many factors are obtained from experiments and other research papers. These factors have different effects on the carbonation depths, and the most important variables are the coefficient of mass transport and the reaction of carbonation. The stress effect on carbonation is evaluated by damage variables. In this study, we choose Sidorov's method to calculate damage variables. And then we use the finite element method to solve these equations. In terms of the simulation result, we assume that one area can be regarded as fully carbonated when relative carbonation degree % or beyond. In 2016, Dr. Han and his team also applied Cetus model to study the carbonation of concrete. Comparing with Dr. Han's research, we choose more reasonable variable values, and our curves are clearly closer to Cetus results. We also carried out experimental studies. It can be seen that the predicted results of the proposed model are very close to the test data, especially after 100 days. In conclusion, the proposed model was verified by both experiments and simulations. In next section, we implemented the proposed model for several investigations. We studied many factors that may affect the carbonation process, such as the aggregate content and the geometries, and the cracks. We also tried to find out how the proposed model performs regarding of different environments, such as carbonation from 2 dimensions, long-term carbonation that lasts for 50 years, and accelerated carbonation with CO2 concentration up to 2% and even 20%. The proposed model has been verified in all these conditions. In the last part, we copied the strength field with the modified model. We use the concrete plastic damage model to calculate the stiffness degradation and imported the result into previous carbonation model. From table 1, we can see that the carbonation depth and the stress ratio of 0.6 increases over 30% comparing with that under normal condition. This indicates that applying load improves the carbonation process. That's all for my presentation. Thank you very much.